Hello, I am Dr. Kulkarni. This presentation deals with the bias in epidemiological studies, and this is the part 1 of the presentation. Part 2 of the presentation is separately recorded and is separately available. The three common problems in epidemiological studies are the random error, the bias, and the confounding. In this presentation, we will be dealing with bias, but a few things about the random error will also be discussed. The problem of confounding will be discussed in part 2 of the presentation. The random errors are statistical fluctuations in either direction in the measured data. So in epidemiological studies, we make an estimate of the variable under question, and the random errors can result in the statistical fluctuations in either direction, meaning that the estimate of the variable will either be reduced or it will be inflated, and it will be larger than what actually it is. The random errors can occur due to the precision limitations of the measurement device or instrument. The measurement device or the instrument could be a laboratory investigation, it could be an imaging device, it could be a physical examination, or it could be a questionnaire or interview. And the measurement device could be measuring the variable not precisely, but has the limitations, thereby imprecise measurements are obtained. And this error, which occurs due to the precision limitations of the measurement device, is called as the random error. This usually results from the experimental's inability to take the same measurement in the same way to get the exactly same reading. We have observed many times that if we take the blood pressure of an individual second time, it may not be exactly same as it was taken for the first time, although the measurement method may be similar. That is, we may have taken the measurement either in lying down position or in the sitting position. Even then, the first measurement and the second measurement may not be identical, and this is because the measuring instrument, that is the sphygmomanometer, may not be giving the precise readings, or the person measuring the blood pressure may not be repeating the steps in the same way as he or she has done for the first time. So the random error, therefore, is a statistical fluctuation in the measurement data due to the precision limitations of the measurement device. The bias, on the contrary, is a systematic error or distortion induced in the study. This can occur during the design, conduct, or analysis of the study. It affects the internal validity of the study. About 50 types of the bias have been described, but we should not be confused with the errors. The bias should not be confused with the errors, and let us see what are the differences in the random error and bias. So as the name suggests, the random error occurs randomly. That's why the name random error is given. So the error occurs randomly. Well, in case of bias, the error is a systematic error, and therefore that's the difference. That's the first difference in between the random error and the bias. The secondly, it is also known as a variability. The random error is also known as variability. There is no other name for the bias. The direction in which the error occurs in case of random error is in two directions. In the same study, the error could occur in one direction as well as in another direction also. So two directional error can occur in the same study. So on some individuals the error may be in one direction, on some individuals the error may be in other direction. So that is the peculiarity of the random error. Whereas in the case of bias, the error is one directional only, and that's why that's how it differs from the random error, because the direction is unidirectional in case of bias, and it is a two-directional error in case of random error. So because it is a two-directional error, if we make multiple observations and average them, the random error is likely to be corrected or it is likely to be minimized, because it is a two-directional error and you average the readings multiple times. If you take the reading multiple times and average them, the random error is either corrected or it gets minimized. But in case of bias, the averaging of the multiple observations doesn't help and it does not correct the bias. So averaging the multiple observations is not the way to minimize or nullify the bias that has occurred in the study. Increasing the sample size may correct the random error, but it does not correct the bias. It may not correct the bias. The increasing the sample size is not a definite way of correcting the random error, but to some extent it may be corrected. But it definitely doesn't correct the error that has occurred because of the bias. The increasing the sample size will not correct the bias. Then the random error corresponds to imprecision in the measurement, whereas the bias corresponds to inaccuracy in the measurement. So the random error introduces the imprecision, or it is because of the imprecision in the measurement, whereas in the bias it is because of the inaccuracy in the measurement. So these are the differences in the random error and in the bias. Then how do we classify the bias? So it can be classified as according to the time when it occurs. It can be classified according to the study design, or there could be a broad classification. So depending on when the bias occurs, one can describe the biases that occur in the planning stage, the biases that occurs in the execution stage of this study, at the time of analysis of the study, at the time of interpretation, and at the time of publication of the study. So at these stages, the biases can occur, and we can describe them at the various stages. What are the biases that occur at the various stages of the study? As per the study designs, we can describe the biases that occur in the cross-sectional study, the biases that occur in the case control study, cohort study, and the experimental study. Some biases are very common in the cross-sectional study and they may not be seen in the case control or the cohort study. Similarly, some biases are very common in experimental study, they may not be seen in the cross-sectional study. So one can describe the biases depending on the study design. The third way of classification is the broad classification, wherein the biases are classified as the selection bias, information bias, and confounding bias. Some people consider confounding as a separate problem, different from the bias. So for them, therefore, there are only two types of broad classes of bias, that is selection bias and information bias, because for them, confounding is a separate problem. But some consider confounding as a bias, and therefore for them, the broad classification will include the confounding bias, and therefore there will be three broad classes of biases, namely selection bias, information bias, and confounding bias. The confounding bias will be explained in the part 2 of the study. Similarly, the information bias will be explained in part 2 of the study. This presentation, therefore, will be limited to the selection bias and the types of the selection bias. So the selection bias is occurs because of inappropriate definition of the eligible population or the groups. So when you undertake the study, you have to define the population or the participants in the study. And this is called as defining in fact, this is a very important step in any epidemiological study, defining the eligible population. And defining the eligible population is done by way of mentioning the inclusion and exclusion criteria. But if these are inappropriate and therefore or if these are ambiguous, then it becomes inappropriate and therefore the eligible population will not be defined clearly, and therefore it becomes an inappropriate definition of the eligible population and the selection bias is introduced. Eligible population may be divided into various groups, like the gender-wise groups, the age-wise groups, the occupation-wise groups, and the definition of these groups may be inappropriate or imprecise, and that introduces another bias, or that is another way by which the selection bias can be introduced in the study. So one way or the one common way is inappropriate selection or the comparison group. The many epidemiological studies like analytical studies and experimental studies include a comparison group. for comparison. And there is a study group and there is a comparison group. So if there is an inappropriate selection of the comparison group, then again the selection bias can occur. This can occur in a case control study wherein the control group is inappropriately selected. So the selection bias is introduced over there in the case control study. Another way by which the selection bias can be introduced is that the observations done on the sample that is not representative of the population. So a representative population is the one which is wherein the sampling method is scientific, and the scientific sampling methods include the probability sampling. The methods that are included under the head probability sampling are scientific methods of sampling. So we know the probability of a person getting included in the sample and the probability of a person not getting included in the sample. So non-probability samplings will definitely cause the selection bias. So in epidemiological studies, we resort to the probability sampling, wherein therefore the sample becomes representative of the population, because the sampling method is a scientific method of sampling, that is the probability sampling method. With this, we discuss the various types of the selection bias. The first to be discussed and described is a healthcare access bias. Access to healthcare differs in different population groups due to various reasons, that is cultural, economic or geographic group. The people may be very poor to go to the hospital. They may not be, going to the hospital may not be within their budget, and that's why they do not go to that hospital. The hospital may be geographically far off from the persons or the people, and therefore there is a geographic inaccessibility of the population. So for those persons who are economically poor or who are geographically far away from the hospital services will be therefore not accessible to these types of the persons. So if you do the studies in such hospitals, they will not be representative of the general population, because those persons who are unable to access the hospital because of the economic reasons, because of the geographic reason, or because of cultural reasons, will not be accessing, and they will be underrepresented in the hospital patients, the patients who are availing the services of the hospital. So it will not be representative of the population for which you are extrapolating the observations from the hospital-based study. The prevalence of the diseases as detected by hospital-based studies and community-based studies would therefore differ. This is because the groups which do not access the healthcare services of that hospital will not be going to that hospital because of the cultural, economic or geographic reasons, and therefore they will be unrepresented in that population, and therefore neither the diseases occurring in them will be represented in the numerator for calculating the prevalence of the disease, nor they will be represented in the denominator, or they will be underrepresented in the denominator. Therefore, the prevalence of the disease as estimated by the hospital-based studies and the community-based studies would differ, and this is because of the healthcare bias. This can result in overestimation or underestimation of the hospital-based studies, depending on whether there is an excess representation or underrepresentation of the population in the hospital, the persons who are availing the services of the hospital. The prevention of healthcare access bias can be done, number one, firstly by accepting that such a bias is likely to occur in hospital-based studies. So we must accept that such a bias is likely to occur, and we should consider these inequalities. A priori sensitivity analysis to determine whether the inequality is a confounder can be done. So before we start the study, we can conduct a priori sensitivity analysis and determine whether this healthcare access bias is there and whether it is a confounding variable. The difference in the accessibility of the healthcare to different cultural, economic or geographic group, whether it is a confounder, that can be found out. And if it is, then the hospital-based studies should not be undertaken for that objective. But if it is not, then it is not a confounder, and therefore we can conduct for that objective the hospital-based studies. So a priori sensitivity analysis to determine if the inequality is a confounder, that can be done. So before starting the study, we can undertake the a priori sensitivity analysis. The second one is the healthy worker effect. This is a special type of selection bias. This term was coined by McMichael in 1976. The term healthy worker effect was coined by McMichael in 1976, although the healthy worker effect was described prior to 1976. This is a consistent tendency which has been observed in actively employed to have a favorable mortality experience when compared with general population by way of standardized mortality ratio. So we compare the particular occupational group with the general population mortality, and the comparison indicator is called as standardized mortality ratio. If the standardized mortality ratio for that occupation is higher than that of the general population, we say that the occupation is resulting in the higher mortality. Whereas if it is less than the general population, we say that the occupation has rather a protective effect. But in many cases it has been observed, in many cases where we know that the persons in that occupation are exposed to detrimental or hazardous chemicals, the events like accidents. So even there also it has been observed that the actively employed group has got a favorable mortality experience. So when it was investigated, it was found that this healthy worker effect is the reason for that. And how does it occur, and why does it occur? It occurs because the occupational groups are compared with the general population, and the general population is a heterogeneous group. General population comprises of the groups like children, like elderly persons, like women who have a higher mortality rate than others. Whereas the occupational group is a comparatively homogeneous group. In fact, it is also a part of the general population. The occupational group is also the part of general population. But it is a homogeneous group. And the general population is a heterogeneous group which comprises of children, elderlies, and the women who have a higher mortality than others. Let us examine why this occurs with the help of this diagrammatic conceptualization of healthy worker effect. So this is general population shown in yellow, and this comprises of children, elderly, women, and adults. Adults do comprise of women, but here for the sake of discussion and description, it has been shown as a different group. So this is the general population, and it comprises of children, elderly, women, and adults, which as far as the mortality is concerned is a heterogeneous group, because children, elderly, and the women have a higher mortality as compared to the adults. So this is a heterogeneous group. But consider this group, the workers' population, which comprises of the adults. It is very rare that any occupation has got children included or elderly persons included in that occupation. So as far as the age is concerned, the workers' population is a homogeneous population. Similarly, many of the occupations, as far as gender is concerned, will also be homogeneous. Many occupations will be seen to employ males only. Many occupations like nurses, will be seen to employ the women only. So as far as gender is concerned, the working population is also a homogeneous population. So as compared to that, the general population is a heterogeneous entity. Secondly, the working population or the occupational groups are exposed to pre-placement examination. This is a sort of filter, and this is applied when the people are brought in from the general population into the working population. And this filter, that is the pre-placement examination, ensures that relatively healthy persons are in the workers' population, and the persons who are denied placement are those persons who are not that healthy. So pre-placement examination selectively sees that the worker population is comparatively healthy as compared to the general population. Even the persons who are suffering from severe disease, with the severe disease, may leave the occupation, And when we undertake the study, they may not be available for the study. They may not be studied in the when we study the effect of the occupation on the morbidity and mortality. So this is one. The persons with the severe disease are excluded when we undertake this study, and they cannot be excluded in general population because they are there in the general population. Similarly, the mortality, the people dying while in this occupation may not be available, and the information may not be available. Information may not be collected when we are comparing the occupational morbidity or mortality with the general population. Many studies do not include this. So on one side, this is a homogeneous group as compared to this. On another side, this is a comparatively healthy group as compared to this because of pre-placement examination, and there is likely to be a selective exclusion of those with the severe disease and mortality from the workers population. Because of this workers group becomes a comparatively healthy, and therefore this is called as a healthy worker effect. So such a group is compared with the population, general population, and this comparison is therefore a comparison of unequals, apples being compared with the oranges. And that's why we should take care to see and find out whether such a healthy worker effect, the bias because of healthy worker effect, has occurred whenever we are undertaking any study wherein we are trying to show a relationship with an occupation with the morbidity or mortality of that group. The effect does not affect all occupational groups equally. So in some groups there may be say 10% increase in the estimate. In some cases there may be 20% increase because of the healthy worker effect. So it is not equal, but it is a unidirectional thing that it will always be showing the occupational groups in favorable circumstances. So allowance must be made. So what should we do? So we should make an allowance for unequal distribution of age, gender and race. So age, gender and race standardization must be done. So standardization with respect to age, gender, race, etc., which are affecting the mortality, must be made whenever we are comparing the mortality or morbidity experience of an occupation with the general population. So that will minimize or that will nullify the healthy worker effect. The second is the volunteer bias. The people who volunteer for the research project, in many research projects, the advertisements are made that people should volunteer in the study. They should come and report at such and such places for registering themselves for that study. So this is the study involving the volunteers. These volunteers are more likely to be health conscious. They are more likely to be literate. They may be practicing preventive measures more and better as compared to those who do not volunteer. They may refrain from reporting negative practices related to disease with the social stigma, like the diseases like leprosy or diseases like sexually transmitted diseases. So because the volunteers will differ in so many ways from non-volunteers, so the volunteers may not be representative of the general population, because general population is a mix-up of these volunteers and those who are not volunteer. So the volunteer population is a selective group who will be differing from non-volunteers and therefore will not be representative of the general population. What is the impact of the volunteering is difficult to ascertain, but it does occur. It is generally agreed that such an effect does occur. And the preventive measures can be taken, that we introduce anonymity, confidentiality in the information. We can assure about the confidentiality so that the people do not refrain from reporting negative practices related to the diseases with the social stigma. So anonymity, ensuring the anonymity and ensuring the confidentiality is one of the ways of reducing the volunteer bias. Then the next type of bias, selection bias, is Bergson's bias, which is described by Joseph Bergson in 1946. It is also called as Bergson's fallacy or Bergson's paradox. So this occurs when both exposure and outcome affect the selection. That is, there is an exposure factor and there is an outcome factor, and both are influencing the selection of the participant. So if the exposure is there and outcome is there, then there is, suppose if there is an additional probability of being selected, then this bias will occur. So with both the exposure and outcome are going to affect the selection of the person in the study, then the Bergson bias is more likely to occur. It typically occurs in hospital-based studies because we try to show a relationship between two diseases, and wherein we consider one disease as an exposure factor or a predisposing factor for the other disease. So here the probability, the exposure factor is one disease and the outcome factor is another disease. A probability that the person will be admitted for the two entities is more in the hospital cases. If the person has two diseases, there is more likelihood of that person being admitted. So while comparing the frequency of two conditions requiring hospitalization, also the Bergson's bias can occur. So this results in a spurious negative or a positive association. Mostly there is a spurious positive association. So the persons with two diseases are more likely to be hospitalized. And if these two diseases are the one wherein we are trying to establish an association, then the Bergson's bias is likely to occur. The hospital sample will therefore show a spurious positive association when none exists in the population. In the population, such a association may not exist, but in the hospital-based sample, hospital-based study, the association will be seen, and this will be an example of Bergson's bias. This table below, table over here, shows the study in which such association was studied. So on this side, on the left side, in general population, this is a 2x2 table, where in general population this association was studied in between the diseases of the bone and the respiratory disease. Whether there is an association of the existence of the diseases of bone and the respiratory disease, this was studied in general population in 2,583 individuals, and 17 individuals were found to have both the conditions. In 2,376 individuals, both the conditions were absent. So this is a 2x2 table which tries to analyze whether there is any association, and the association is examined with the help of odds ratio, and the odds ratio in this case has been found to be 1.06. So it shows a very weak association, or probably if it is the statistical significance is seen, it will turn out to be statistically not significant association. 1.06 practically means no association. A subset of this data is examined on this side of the table. In the subset who were in the hospital in the prior 6 months. Out of these, those persons who were in the hospital in the prior 6 months. And this looks like a study, hospital-based study, for this objective of showing the association between diseases of bones and the respiratory diseases. And herein we found five individuals having both, that is the respiratory disease and the disease of the bone and the organs of movement. And 219 individuals did not have any of these two. And the odds ratio in this case was 4.06. So quite a high odds ratio. The number indicates that the strength of association is positive, and quite strong association is there. If you apply the statistical test of significance, we may find this to be significant. So we find over here a strong positive association when the study is made in the hospital, and we find weak and non-significant association when the study is made in the general population. So this has occurred because a person with the locomotor and the respiratory disease is more likely to be admitted in the hospital. A person who has only one of these two is less likely to be admitted in the hospital, and that's why a positive association has been seen in the hospital, and such a positive association is not seen in the population. And this is a classic example of the Bergson's bias or Bergson's paradox. Niemann's bias is another type of selection bias which occurs due to wrong exclusion of very severe cases, very mild cases, or both. If you exclude because of your study design or inclusion and exclusion criteria, because the inclusion and exclusion criteria are set in such a way that you exclude very severe cases, very mild cases, or both, If these are excluded, then the Newman's bias occurs. Newman's bias is said to occur if these two, any one of these two or both have been done. Excluding the severe cases will lead to disease looking very mild. If the severe cases are excluded because of your inclusion and exclusion criteria, the disease will look very mild. If because of your inclusion and exclusion criteria, we have excluded the mild disease, then the disease will look very severe. So on one side, it may look very mild, on another side, it may look very severe, and the results therefore may become very skewed. And we want to avoid such a skewed type of distribution in the estimation of the variable in the research question. So it also occurs when there is a time gap in the exposure and the study. The longer the time between the exposure and the study, more likely the Newman's bias is to happen. So let us examine this issue in a moment. Therefore, the study of the patient, the Newman's bias, there is another way by which the Newman's bias can occur, is if we, for example, undertake the study on the patients who are admitted at the time of the study only. Only those who are admitted at the time of the study, diarrhea patients who are only admitted, whether they are discharged, whether they are died, we are not bothered, but only those who were in the hospital at the time of your study. So that is our inclusion criteria. So the study of the patients, diarrhea patients, only admitted at the time of the study. So those cases who were admitted at the time of the study are included. So such inclusion criteria may miss or will miss definitely the patients who die because of the diarrhea and the patients who recover because of diarrhea. So if the inclusion criteria are that the patients admitted for diarrhea is the inclusion criteria, without mentioning that whether the patients who died and recovered and were discharged will be included or not. So that will be an improper way of inclusion criteria, and the Newman's bias will therefore be introduced in the study. So this bias is therefore less likely to occur in acute disease like diarrhea. The diarrhea is the example given over here, but it is less likely to occur in such cases, acute diseases, and it is also less likely in the cohort study. But it is more likely in the chronic disease and more likely in the case control study. Let us examine why it is more likely in the chronic disease with the help of this diagram. The Newman's bias is also called as prevalence incidence bias because the bias occurs when we include only the prevalent cases. So that's why it is also called as a prevalence incidence bias. And it relates therefore to the timing when the cases are admitted with reference to the starting of the study time. So these are the two situations, situation A and situation B is there. And this is the time when, this is the timeline, and this is the time when the exposure has occurred and the outcome has occurred. And this duration between the exposure and the outcome is called as induction time. And this is similar in both the cases. In the A and B, the same situation is there. The induction time is the same in both the cases, either the situation A or situation B. But in situation A, the study starts very close to the outcome of the disease, or outcome, that is the disease. So these are new cases because the duration between the outcome and the starting of the study is very short. So these are practically new cases. But in this case B, here the outcome has occurred at this point of time and the study has started at this point of time. So this is the time gap between the study starting and the outcome has occurred. So practically this is an old case. This is an old case, or in terms of epidemiology, these cases may be called as a prevalent cases. So here the study includes practically the new cases. Here the study may include the new as well as the old cases. What happens in this case, in situation A, the duration between the study, which starts over here, and the exposure is comparatively very small. Although the induction time is same in both the cases, because the study has started immediately after the outcome has occurred and the new cases is included, the duration between the outcome, between the starting of the study, this point, and the exposure, this point, is comparatively less. In this case, here the study has started and the exposure has occurred at this point of time. So this is the duration between the study time and the exposure time, and this is the duration between the exposure and the study starting time. This is shorter in situation A, and it is quite long in case of the in situation B. So when you include the old cases or prevalent cases, there is likelihood of this gap more. And when you include the incident cases or new cases only, the gap between the exposure and the study start is comparatively very small. And that's why in case control study, which starts after the outcome, the case control study by definition are the studies which are undertaken after the exposure and the outcome has occurred, and the study starting point is over here, or over here, something like this. So in case control studies, therefore, we expect, and the dictum is that we include the new cases only rather than old cases. So the case control study, the situation is like A. In cohort study, on the contrary, the study starts at this point of time. That is, it starts before the outcome has occurred and after the exposure has occurred. And we follow this till the outcome has occurred in cohort study. So the duration is less as compared to the case control study. So the duration between the exposure and the study starting is less in cohort study than in the case control study. So this bias, which is called as the prevalence incidence bias, is less likely to occur in case of the cohort studies. It is likely to occur in case of cross-sectional studies. So how do we prevent the Niemann's bias? The first is you use the incident cases only instead of prevalent cases. So the possibility of Niemann's bias is reduced. So we include all grades of severity. We, instead of including only the mild cases, instead of including only the cases that are admitted, we include all shades of severity of the cases. So that reduces the Niemann's bias to some extent. And consider including those who die and those who recover. So if we include those who die and recover in the study design and in inclusion and exclusion criteria, then the Niemann's bias is less likely to occur. The spectrum bias is another selection bias which occurs while evaluating the performance of a diagnostic test. So this is peculiar for the evaluation of the diagnostic test. And if you are comparing the diagnostic test, its specificity and sensitivity in two hospitals, and you may find a gross dissimilarity in between the sensitivity and specificity, although the test is the same and although the application criteria may be the same. Why does this occur when you are comparing the sensitivity and specificity of a test when you are comparing it in two hospitals? So why does it occur? It occurs due to the difference in clinical spectrum of the disease in two hospitals. The two hospitals may be catering to the disease which has got different spectrum. The spectrum of the disease in first hospital and the spectrum of the disease in the second hospital may be very different. And what are the aspects of the spectrum of the disease that cause this spectrum bias? Let us evaluate. It is because of the three aspects of the spectrum. The first aspect is that the difference in the spectrum of the target disease. Suppose you are comparing the sensitivity and the specificity of the test for AIDS, and there are two hospitals. Wherein you are comparing the sensitivity and specificity of the test, of a diagnostic test, in two hospitals catering service to the AIDS. So AIDS is the target disease. So what is the spectrum of the disease in first hospital, spectrum of the target disease? The target disease in this case is AIDS. So what is the spectrum of the disease? That is the target disease, that is the AIDS in first hospital. And what is the spectrum of the disease in the second hospital? If it is widely different, if they are catering to different spectrum, entirely different spectrum, like for example, one is only providing the hospital-based services for severe cases, mild cases, moderate cases, all grades of severity are there included. Whereas another hospital is catering only the OPD-based services, that is for the mild cases only. So one hospital is catering services to all grades of severity, another is catering services to the mild cases only. So the spectrum of target disease in these two hospitals is different, and this will affect the sensitivity. This will not affect the specificity of the disease. The second aspect of the spectrum is what is the spectrum of the persons without the target disease. Because for evaluating this diagnostic test, we have to perform that test on the target disease, persons having the target disease, and the persons not having the target disease. For that also, on those individuals also, we have to apply the test. Now, in case of two hospitals, for example, if one is a general hospital, one is a very general hospital, and one is a specific hospital catering services only to the AIDS. So over there, it will be very difficult for us to find the persons without the target disease, and therefore the person will have to make huge time and efforts will have to be spent in that hospital to find a person without the target disease, without the target disease, that is the AIDS or HIV infection. So if this aspect is differing in the two hospitals, that is the spectrum of those without the target disease is differing, then this will affect the specificity of the test. The specificity of the diagnostic test will be different in this if the two hospitals are differing in this aspect of the spectrum. If the hospitals are catering to the populations in which the prevalence is markedly different, one is where the disease is very rare and one is where the disease is very common. So if the two hospitals are there and the one is catering to the population wherein the prevalence is very low and another is where the prevalence is very high, then in such situation it will affect both the sensitivity and the specificity. So you can find therefore that when you are comparing the specificity and the sensitivity of a diagnostic test in two hospitals, these are the aspects of the spectrum that you will have to take into consideration, and these will have to be matched, these will have to be adjusted in the analysis or in the planning stage. These will have to be adjusted to, and then only it will be a valid comparison. Otherwise they may show the difference in the sensitivity or the specificity, or they may show the difference in both. The prevention is to examine the heterogeneity of the subjects. So one should know the background of these hospitals. What is the spectrum of the target disease in the two hospitals? What is the spectrum of the patients without the target disease in these two hospitals? That must be examined. And what is the prevalence in these two hospitals? Prevalence in the community for which they cater to. So if you examine these and then adjust accordingly, the spectrum bias is less likely to occur. So these were the various types of the common types of the selection bias, and the common strategies for prevention of the selection bias will be discussed over here. So first of all, one must have a scientific sampling method, and the methods that are called as probability sampling are the scientific sampling methods. So if you resort to non-probability samplings, then the selection bias is bound to occur. So resort to scientific sampling methods, resort to the probability sampling methods that are described in the literature. Second is sample size determination. People determine the sample size without making any provision for the design effect and the loss to follow. The sampling size methods are based on the assumption that your sampling is as per simple random sampling. But if you are not resorting to simple random sampling, then you have to make correction for the design effect of your study design, and the correction has to be implemented, and the sample size has to be adjusted accordingly. The provision also has to be made in loss to follow-up. This is especially for follow-up type of the studies like longitudinal studies, cohort studies, or the experimental studies where the follow-up is there and there is a loss to follow. So one has to make an intelligent guess, learned guess about the loss to follow, and the sample size has to be increased for adjusting the loss to the follow. one has to make thoughtful inclusion and exclusion criteria. If the inclusion criteria are too broad, then there is a possibility that those who are not having the target disease will be included in the participants, and there will be selection bias introduced over there. If your exclusion criteria are too stringent, then there is a possibility that you will miss many persons having that disease. You will be missing either the mild cases, or you will be missing very severe cases, and therefore a selection bias will be introduced. So don't introduce, or don't have too liberal inclusion criteria, don't have too stringent exclusion criteria. the the scientific allocation methods in experimental studies, you allocate the participants after having selected them, you allocate them to the study group and to the control group. So the allocation methods are there for allocating the persons to the study and the study group and to the control group, and one must resort to the scientific allocation methods, and blinding is another way by which the selection bias can be minimized. The blinding is a technique which is introduced in the clinical trial. It may not be possible in all clinical trials to introduce blinding, but wherever possible, one must think of introducing the blinding in order to minimize the selection bias. After the data is collected, one can adjust for possible selection bias in the form of intention to treat analysis. At the phase of analysis in clinical trials or in experimental studies, you can have what is called as intention to treat analysis. This sort of analysis is supposed to take care of or minimize the selection bias. The second thing that can be done in the analysis phase of the studies is missing data analysis. This can be applied in all types of the clinical trials. The data may be missing. For certain cases, the data may be missing for some variables, and there may be disproportionate missing of the data in the study and the control group. So missing data analysis can be done at the analysis phase. This is not in the planning stage, but at the analysis stage. So if the data is suppose missing for a particular variable, then you can carry forward the last variable. The variable is, say, bacteriological examination, and some persons have missed the bacteriological examination. So the one method is carrying forward the last bacteriological exam. Results of the last bacteriological examination are carried forward. Or you can carry the baseline value as the current value at the time of follow. So these are the two methods which are introduced in the missing data analysis, which can to some extent do with the selection bias. Then sensitivity analysis is another method of dealing with the missing data, and this involves having a worst case scenario and the best case scenario. So we construct a worst case scenario and we construct the best case scenario and try to find out whether there is a difference, and if there is a difference, probably it is because of the selection bias. So at the time of the planning of the study, at the time of the analysis of the study in the form of intention to treat analysis, in the form of missing data analysis, we can to some extent deal with the selection bias. So this, friends, finishes the discussion on the selection bias in the part 1. In the part 2 of the study, we will be discussing the other types of the bias, that is the classification bias and the confounding problem in the epidemiological studies. If you have got any problem regarding this presentation, you can contact me at this email ID drapkulkarni@gmail.com. Thank you very much.